Hello everyone, Assalamu alaikum. We are home group 3. In this video we will explain how the filtering process has been completed to remove a noise from the audio signal. First we will start with our objectives. So the first objective is to remove the noise that corrupting the audio signal by designing a suitable filter. And the second, we will graphically represent the signal in the time domain and the frequency domain. So before we start the filtering process, we need to draw the audio signal in the time domain as shown in this slide. So the y-axis is represent the amplitude and the x-axis represents the time. So after we draw the audio signal in the time domain, we need to convert it from the continuous signal into discrete signal. And also the audio signal is represented in the frequency domain by using the fast Fourier transform command.
Now, let's moving forward to filter design. First, we have to identify the noise present in the original signal. By just hearing at the original signal, we can learn that there is at least two noises which contributing to a beeping sound and a ticking sound. Now let's look at the frequency domain graph. In this graph, it is obvious that the noise is located at 800 frequency, but there is no sign of the other noise which contributing to the ticking noise. To tackle this problem, our team had decided to use another approach, which is the spectrogram. Now let's look at the spectrogram in the figure below. The two noises which contributing to the beeping sound and ticking sound is found to located at 0.2 normalized frequency and above 0.6 normalized frequency. By converting the normalized frequency to the real frequency, we can times the normalized frequency by half of the sampling frequency, which is 4000 Hz. By doing so, we can get that one of the noise is located at around 800 Hz and the other one is above 2400 Hz. After successfully identifying the two noises, now we have to design a filter. First, an IRR bundle bandstop filter is selected to remove the high-pitched noise at around 800 Hz. The order of the filter is 4 with a low cutoff frequency at 795 Hz and a high cutoff frequency at 805 Hz. The IRR filter is selected because it will provide a fast response with a high drop-off rate so that the input signal will not be distorted that much. After that, another FIR Blackman low-pass filter is selected to remove the noise above 2400 Hz with an order of 50. The FIR filter is selected to make the system more stable due to the fact that the constant phase shift and delay. Filter properties in the MATLAB is shown in the figure below. After the convolution of these two filters, the dot plot of the overall filter is shown in the figure on the right. Now, I will pass to my friend to explain the properties of this filter.
Good day, and I'm Yun. I will present the stability of the filter using Z transform. The stability of the filter can be examined by the pole zero plot, plus the convolution of AK between the Butterworth filter and FIR filter, and the convolution of BK between the Butterworth filter and FIR filter are done using the MATLAB code Q equal to conv VAFA and P equal to conv VBFB to represent the convolution of AK and BK. Plus, we do the Z-plane PQ to plot the pole zero plot. From the pole zero plot, there are 4 poles with conjugates. So the Butterworth filter is the 4th order bandstop filter. And there are 49 poles in the origin. So we know that the FR filter is the 50th order. Based on the pole zero plot graph, we know that the poles are inside the unit circle. Thus, we can conclude the system is stable. Next, the impulse response of Hn is plotted in MATLAB using stem Hk, where Hk is equal to IMPZ PQ50. P and Q are found before, where 50 is the length of the filter. Generally, the overall filter is the convolution between the Butterworth filter and the Blackman filter, which is the FIR filter, due to the filters are connected in the cascaded form. The graph before signal filtering and the graph after signal filtering in time domain are plotted using the MATLAB codes as shown below. The frequency domain H omega before and after signal filtering are plotted using MATLAB. The red frames show the noise signal while the green frames show the noise removed. The graph before and after signal filtering in time domain are shown, where the red circle represents the noise signal before the signal filtering and the yellow circle is represent the signal after filtering. So let's hear the signal before filtering and the signal after filtering.
0125 0125
That's all from Home Group 3. Thank you.